Dear students, today we discuss about the magnetic effect of electric current. What is magnetic field? It is an area around a magnet in which there is a magnetic force. It is a magnetic force of lines. It is called magnetic field. This natural magnet consists of a positive charges and the negative charges. They consist of the orderly arrangement of dipoles. These dipoles, the orderly arrangement of dipoles creates the magnetic field. This field is due to V's molecular field. This is the molecules and the atoms, that is the dipoles, are arranged in a ordered manner. So they produce the pole, one pole here and another charged pole in this side. So this side is on the north side, it is south side. So this magnetic lines of force spreads around the magnet. This area, this field, this force, called as the magnetic field. In the same way, we can also create the artificial magnetic field when a electric charge, the electric charges, electron or positron, can create a magnetic field. When the electric charge, electrons, move through a conductor, when an electron moves through a conductor, it also produces the magnetic field. The unit for the magnetic field is called Tesla. It is the Fleming right-hand rule. It is the conductor. It is the current is passing through this line. This thumb indicates the direction of current. So the magnetic field produces like this fingers, other fingers. So the magnetic field produces around the conductor like this when current I passing through this direction in the conductor. So the electric current produces a magnetic field. So this is indicated by B. So what is magnetic flux? A magnetic flux, it is indicated by symbol phi. It is a measurement of total magnetic field passes through given area. It is the magnetic field lines of force. It is a magnet. It is a magnetic lines of force. We are placing a flat surface, a simple metal flat surface. So this is just inclined to some angle. It is inclined. It is the magnetic field lines of force. They are magnetic lines of force. It is the normal, a perpendicular line drawn, perpendicular line drawn to the lines of force. It is a line drawn to perpendicular to this lines of force. So this line is called normal line. Normal line. So the magnetic lines of force passing through this area, it is the flat area. In this area, the lines of force passing. So we are choosing a simple flat surface with the area A. This is a test area and inclined to the angle theta between the normal and the surface. So a magnetic field vector B is passing through this. So the magnetic flux, so that total, it is a measurement, the measurement of magnetic field passing through this area. So the magnetic flux is calculated as the magnetic field B and the area A and the angle. See here theta, here the cos theta, this area and this one. It's called cos theta. So phi is equal to B into A cos theta. Suppose the flat surface is not inclined. It is inclined to angle theta. So we will have the equation phi is equal to BA cos theta. Suppose this flat surface is parallel to normal, a line drawn perpendicular to the magnetic field. So this angle theta becomes 0. So cos 0 is 1. So phi is equal to B A. So this equation is modified into B into A. And then the same flat surface is placed parallel to the magnetic lines of force. This is parallel to magnetic lines of force, and it is inclined 90 degree to the normal. The normal, that is a perpendicular line drawn to the magnetic field. So it is parallel to magnetic field. Here the theta gets the value 90 degree. So cos 90 is 0. So we get phi. Yes. So the magnetic flux is 0 when a surface is placed parallel to magnetic lines of force and perpendicular to normal drawn. In this connection, there is a law called Biot-Savart's law. Derive Biot-Savart's law. Suppose we are considering a conductor, a wire or conductor X and Y, which carries the current I. In this wire, we are considering a small part, a small element called AB of length dl. Its center point is O. Consider another point P at a distance R from A. So when the current is passing through the wire, this area, it produces a magnetic field in this area. Suppose when the current is passing through this conductor, it produces a magnetic field. The magnetic field due to this portion AB, this element AB, will create a magnetic field like this. So the magnetic field produced, the magnetic field measured at the point P, it is directly proportional to the current passing through the wire, and the length we have taken for this experiment dl, and it is inversely proportional to square of the distance between them. If the point is nearer to this element dl, the magnetic field, the magnetic flux will be high. When the distance increases, when we go away from the element AB, the magnetic field is decreases. So it is inversely proportional. So we are combining this. So change in magnetic field dB is directly proportional to current and directly proportional to the element length and inversely proportional to square of the distance between them. And so the dB is directly IDL. The DL is taken as sin theta. Suppose it is inclined to some angle. This is taken as sin theta by r square. So dB is equal to this, the proportionality constant mu naught 4 by IDL sin theta by r square. So this is the equation describing the magnetic field generated by the constant electric current. So the magnetic field produced by the current passing through this. It relates the magnetic field to its magnitude, direction, length, and relationship of electric current and magnetic field. So the mu naught is the permeability of the free space. it have the value 4 pi into 10 power minus 7 Newton per ampere square. So this equation relates the magnetic field to its magnitude, direction, length, and relationship of electric current.